In this video, I'm going to cover section 2.4, error analysis for iterative method. So we're gonna focus on more the error analysis um, and for the iterative method. Okay, so more mathematical theorems and mathematical backgrounds to figure out the error estimate of the method what we have learned. So here's the objective. We're going to investigate the order of convergence functional iteration scheme. Okay, it's type of should be scheme. Okay, so the Newton's method and the secant method and the fixed point iteration method. These are called the functional iteration method, right? And then second objective is to learn the rediscover Newton's method as a mean of obtaining rapid convergence. So and then yeah, so the we're gonna study why Newton's method, I mean, has the fast convergence rate. Okay, so now third one, we're gonna study ways to accelerating the convergence in Newton's method. So is there any way to accelerate the convergence, a rate of convergence? Okay, in the Newton's method. So here, first we need to what study the definition of order of convergence. Okay, so this is really important. That's a really basic and the fundamental definitions before studying um, required. Okay, before studying the error analysis. Okay, so now suppose that the Pn, the sequence of approximation, right? This sequence approach P with the Pn is not equal P for any n. And then suppose that there exists the lambda and then alpha is in the R. And this is a positive real number, okay? So alpha is a positive real number such that limit of Pn plus or minus P absolute value over absolute value of Pn minus P to the alpha power is equal to lambda as it approaches infinity. Okay, so assuming these two statements, then the sequence converges to P order of alpha. So now the order of convergence, the 1 or 1.5 or 2, 3, that means that number representing the conversion order of convergence, the alpha in that formula, okay? Limit of that fraction. You see the alpha in the bottom? That is called the order of convergence, okay? And then with the asymptotic error, constant lambda, okay? Asymptotic error, constant lambda, okay? So now on iterative scheme, Pn is equal to 0, Pn minus 1 is said to be of order of. You see that here, that one is this is the Pn is equal to 0, Pn minus 1. That's the what? That's the core algorithm of the fixed point iteration method, right? Okay, in the special case of if we define, if we define G as the what, the x minus f of x over f prime of x, that's the Newton's formula, then we're going to get the Newton's method. That's going to be Newton's method, okay? So Newton's method is special case of fixed point iteration method. Now, see, okay, of order alpha, if the sequence approach P, okay? So now this P solution, okay? The dual P, yeah, definitely, okay? So of order alpha, so it means that limit of Pn plus or minus P over, absolute value over absolute value of Pn minus P to the alpha's power equals lambda. Okay. So now third one, in general, a sequence with a higher order of convergence converges more rapidly than a sequence with a lower order. Okay. Yeah. So the alpha is alpha is getting bigger, then it means that the method converges faster and faster. Okay, so if alpha equals 1, okay, and the lambda is less than 1, the sequence is linearly convergent. Okay, so that means the what the Pn, in the Pn is n is number is range increase, then the convergence or the convergence of that sequence approaching P is linearly increase. Okay, and the alpha equals 2, and the sequence quadratically convergent. It means that the iterations increase. Okay, 1, 2, 3. So the P1 the sequence is Pn. The n goes to infinity. Then the what? The accuracy. I mean, the sequence approach P quadratically. You know the graph of quadratic function, right? So now why do we have to find the method that produce higher order convergence sequence? Okay, so yeah, I already explained here, but let's see mathematically. So mathematically, we suppose, okay, let me explain why higher order method converge the P exact solution faster than linearly convergent. Okay, so let's see, P and the sequence is linearly convergent to 0 with this. Okay, suppose that, okay, we'll assume that the sequence linearly converges to 0. It means that P, so here now 0 means P. Okay, so that means limit of P absolute Pn plus 1 minus 0, because we don't have to mention the 0. Okay, so we skip the writing 0 over absolute Pn to the alpha. Here the alpha is 1 because the assumption says that what the sequence is linearly convergent. It means that alpha equals 1. Okay, all right, that is 0.5. Okay, that assumption. Okay, 0.5, this is assumption. Okay, so now alpha is 1, lambda is 0.5, and the P equals 0. And now think about the other the sequence Pn tilde. Okay, Pn tilde quadratically convergent to 0. It means and with the limit of that fraction. You see the 2 right there in the bottom. Okay, so that's the meaning of the sequence is convergent, quadratically convergent. Okay, 0.5. Now assume that Pn plus 1 over Pn is approximately 0.5. Yeah, okay, so approximately, we can say that, okay, because the limit of this guy approach n goes infinity 0.5. It means that in certain, for a certain value of n, this is, can be considered as approximation 0.5, okay, close to 0.5, okay. And this also consider that this is approximately 0.5. Now, for the linearly convergent scheme, this means that Pm absolute Pm minus 0 is equal to absolute Pn, approximately 0.5 times Pm minus 1. Yeah, makes sense, right? Okay. So now then, why? Okay. We see, I mean, why how we get this? Because you see that we assume that, that fraction is approximately 0.5. Okay, so that's what we got this. Okay, well, I mentioned that right here. Okay, now the Pn minus 1, Pn plus 1 over Pn, absolute value. Pn plus 1 over Pn is approximately 0.5. It means that what? Pn over Pn minus 1 is approximately 0.5. So we apply what? This formula and this assumption with n and n minus 1 into here. Then we're going to get 0.5 squared times Pn minus 2. Keep going. We're going to get 0.5 to the nth power times, absolute P0. Right? It makes sense, right? Now now we'll see the case that the other sequence P and tilde that is quadratically convergent to 0. Okay, so now where is the quadratic convergence procedure has this? Okay, think about this, P and tilde minus 0. Okay, so now then that is equal to P and tilde. This is approximately 0.5 times Pn minus 1 tilde square. Okay, why we got this? Because see that here. Yeah, we assume that, well, because of that assumption, limit of, that fraction is equal to 0.5. It means that Pn plus 1 tilde over Pn tilde square is approximately 0.5. You see this one? So move the bottom to the right-hand side, then, yeah, so then we're gonna get this. The Pn minus 1 tilde square gonna be 0.5 times Pn minus 2 tilde square and square. Okay, so where squares? Well, we got the double square because of that square goes right here. Okay, and then the reason that we got square because of this. Okay, we just move the denominator into the right hand side, so we're gonna get 0.5 times the Pn minus 2, right? Okay, tilde. Okay, square. Okay, you may say that, okay, this is a Pn minus 1. Why we got the Pn minus 2? we, think about this, P and tilde, apply to apply that, the approximation to that one, we need to modify the n to n minus 1 and n minus 1 to n minus 2. Okay, stop loading. Okay, so that's why we got the n minus 2 right there. As you keep going, then see, then what? Keep doing that. So we're gonna get what? Point final in the here we got 0.5 third power and the Pn minus 2 tilt fourth power, and then Pn minus 2 tilt gonna be 0.5 times Pn minus 3 tilt square, and then there's force power right there. So we're gonna get force power in the outer bracket. Then we're gonna get we have 0.5 third power. Okay, so what? Finally, we got 0.5 to the seventh power, and then Pn minus 3 tilt to the eighth power. Let's see. Now you see the look at this square. You see, and then force power. Okay, eighth power. Now what? We're gonna get the 16th power. So keep doing that. That you're gonna get the final. We're gonna get 2 to the nth power. Okay. So now you see and then 2 to the nth power minus 1 right there, because you see that starting from 1 is the 0.5 to the first power, third power, and then seventh power. Okay, 1 3 7, and then what? 11, right? And then keep going, right? Okay, so now then see. Okay, now let's see. So we got this. That's the additional explanation. Okay, if you don't get it, well, we got this one. Just look at this. Okay. So now let's see which one is let's see, look at this. We compare this. 0.5 to the nth power times this one with 0.5 to the 2n to the nth power minus 1 times tail to the 2 to the nth power. Which one go approach to 0 faster than the goes to approach faster than the other one? This one goes to this one approaches 0 faster than this, right? Okay. For example, let's say n equals 10. 5 times to the 10th power, or 0.5 times 2 to the 10th power minus 1. Which one, is close to 0 than the other one? This, right? Okay. So now then, see why, quadratic convergence, okay? Or this is called quadratic convergence, order convergence is, you know, is a method uh, converge to the exact solution faster, really faster, okay, faster than the linear convergence method, relatively. Okay, so now quadratic convergence sequence are expected to converge much quicker than those that converge only linearly. Yes, we saw that. Theorem 2.8. Let function g is in the closed continuous. Okay, this is let's say g is a continuous function and closed interval a comma b, and then its range is equal to domain. Okay, so now let's see. And then for any x in the domain, suppose that g prime is continuous, and then there is k, and then the attribute of g prime is bounded by k. Now you see that this is what exactly same as the assumption in a fixed point iteration method. Okay, you see, and then if g prime is p is not equal to 0. Okay, now we put this one. What we haven't seen that additional what assumption in the the theorem in Newton's method, right? Okay. So now the sequence Pn equals 0, Pn minus 1 for n is greater than or equals 1. Then this one converges only linearly to the unique fixed point P. Okay. So now let's see. So now let me see. Okay, so this is the, give me a second, that's one. That's the, what? So the theorem 2.8 says that fixed point iteration method converges linearly. Okay, so now here's a proof. By the theorem, fixed point theorems, the sequence Pn approach P, yes. And then since G prime exists, we can apply mean value theorem to G to show that for any n, there exists cosine n. You know the mean value theorem, right? What's the mean value theorem? Mean value theorem is, yeah, I think I told you so many times about mean value theorem. So please the memorize and the fully understand, okay, every single theorems and definition listed in the section chapter 1 in the textbook. Okay, keep in mind this. So now there is cosine and what the slope of the secant line at cosine n is equal to what? Slope of the secant line passing through the p comma what p GOP and the pn comma GOPN comma pn plus 1 comma GOPN, okay, is equal to the slope of the secant line at cosine n. Okay, so what that means, see that here, give me a second. Yep. So okay, let's see. Okay, right. So if you move this one to that one, pn minus 1 to the left hand side, we're gonna get pn minus p, right? Is it? What is this? This is the slope of the secant line passing through what? P comma GOP and the Pn comma GOPn minus 1. This is there exists cosine n such that G prime cosine. What's this? This is slope of the secant, slope of the tangent line at x is equal to cosine n. So Mimiya theorem guaranteed the existence of cosine n. Okay. All right. And then we'll move the bottom one to the right hand side. So that's what we got, that equation. And the GOPN minus 1 is what? The GOPN is equal to P sub n plus 1, and the GOP is equal to P. That's the definition of the function G, right? So now then we got this Pn plus 1 minus P is equal to G prime cosine n times Pn minus P. Okay. Now then the sequence Pn approach P, right? Why? By the fixed point theorem. Okay. So how can we apply fixed point theorem in here? Because the, you see we saw that, the theorem uh suppose that, assumption in that theorem is exactly the same as assumption in the fixed point theorems. Okay. So now we can guarantee that the sequence approach P, and then cosine also approach P. Why? How come? Because you see that here. What? Give me a second. Yeah, because the what? Secant line. I mean, you see here, the secant line. I mean, the slope of the slope of the secant line. In the slope of the secant line, the p comma GOP passing through p comma GOP and pn comma GOPN is equal to the slope of the tangent line cosine n. But if pn approach p, then the secant line approach tangent line at cosine n, right? Right. So that means cosine n approach p. Or if you don't understand, that's fine. Then look at this. Cosine n belong to pn comma p. But what if pn approach p? Then that interval becomes what? Just one number p. But cosine n belong to that interval, so it means that cosine n approach p, right? Okay, either way, that's fine. Okay. So now then, since G prime is continuous, yeah, okay, that's assumption in the theorem, right? The limit of G prime cosine n is equal to G prime p. Yes. So what that means? So if G prime is continuous, then limit can go inside of G prime. Okay. So what that means? You have learned this one in the calculus 1. So that is equal to, see that this one is equal to the limit of, okay, the G prime of not limit. I'm sorry. This is equal to G prime and the limit of cosine n. Okay. If the function is when you if function is a continuous, then the continuous function of the sequence, the limit of continuous function of sequence is equal to limit of continuous function of sequence is equal to the continuous function of limit of that sequence. Okay, that's one of the property of the limit with a continuous function. So, but limit of g cosine is what? P. Okay, so so what? Limit of this guy is equal to g prime p. Yes. Now then, limit of pn plus 1 p minus p over pn minus 1 is equal to, we haven't seen that what by the MVT Beamville theorems, that is equal to what? G prime cosine n, and this is equal to g prime p. Right? Okay. So let's see. Give me a second. Okay. So now then what? Limit of in limit of this fraction is equal to limit of this is equal to g prime p. The limit of absolute value is equal to what? Absolute value of g prime is this obvious. Thus g prime p is not equal to 0. Thus if g prime p is not equal to 0, then fixed point iteration exhibit linearly convergent with an asymptotic error constant absolute value of g prime p. You see that? Now you see here, this is what exactly same as the what? That form exactly same as the form of definition of order of convergence with alpha equals 1. Okay, this makes sense, right? So now here's a note. Now here's a note. Theorem 2.8 implies that higher order convergence for fixed point method of the form g of p equals p can occur only where g prime p equals 0. Additional condition to ensure the quadratic convergence. So now you see. Now give me a second. Give me a second. You see that g prime p is not equal 0. See that right there? Oops. Okay. So give me a second. Excuse me. Yeah, you may find it challenging to understand the why g prime p equals 0. That assumptions lead the order of convergence to 1. So why the to get the higher order, I mean quadratic the convergence rate, to earn the quadratic convergence rate, we have to remove that assumptions. So because c g prime p is not equal to 0, I mean g prime p is not equal to y, we have to remove that assumptions. It means that why we have to assume that g prime p equals 0 to get the quadratic convergence rate. So let's see, but that's related to Taylor series. Okay, so think about this. Theorem 2.9 and Theorem 2.8, the goal is to get the form shown in the definition of order of convergence. See the limit of that fraction right there. So the goal is to get this form, and then you see that right there, the degree of the denominator, that's going to be order of convergence, right? By definition of order of convergence. So theorem 2.8, theorem 2.9, both in the proofs the they are trying to construct the that form, limit of that fractions. Okay, so anyway, see, first one, see that p be a solution of equation x equals 0x. Okay, and then g prime p equals, see that here g prime p equals 0. That's a big difference between the theorem 2.9 and theorem 2.8. Okay, now and then the other one, additional assumption right here. Second derivative g is continuous on an open interval I containing p, and then the second derivative is bounded by m. Okay, on I. Okay, so now then there you just delta such that for any p0, p minus delta comma p plus delta. Okay, so there delta. Okay, let's see. So now then the sequence, okay. So now Pn is equal to Pn minus 1. You see? Let me see. Give me a second. Okay. Pn minus 1, that converts at least quadratically to P. For sufficient large value n, Pn plus 1 minus P is bounded by m over 2 times Pn minus P squared. Okay. So now you see that. Give me a second. Let's see. Yep. So here's a proof. First one. Okay. So we're gonna choose k between 0 and 1 and delta. Okay, such that g prime is bounded by k. Okay, g dou prime is continuous on p minus delta, comma p plus delta. That should be included in over I. Okay, given in over I. So now then g prime is bounded by k, which is less than 1. Okay, then the argument used in the proof of theorem 2.6 showed that g of x map here to here. Actually, you know what, this one, there exists delta, for any p0. We haven't seen this one in lemma in theorem 2.6. Okay, if you don't get it, just please go to the theorem 2. Proof of theorem 2.6. Okay, so I'm not gonna cover that one again. So now this one map from here to here. Okay, so then now then the sequence is included what p minus delta comma p plus delta. So expanding g of x in a linear Taylor polynomial for x. Okay, that gives this the Taylor series. Okay, so now we express function g of x as linear Taylor polynomial. Okay, so why do you say linear? Because the last term is what we're going to consider. Last term is this is what remainder term, right? Now then, see that we assume that g prime p equals 0. So second term is gone, right? Okay, so now that we got this, g of x is equal to, and the g of p equals p, right? That's what the definition of g, right? So g of x equals p plus second derivative g over 2, okay, right there. But we assume that the second derivative, g dou prime is bounded by m, right? Is it? And then so when x equals p sub n, so replacing x by pn p sub n, okay? So g of pn, which is equal to p sub n plus 1, is equal to p plus this one, right? So now then what? But since g prime is bounded by k, and then g maps that closing number to itself, and then fixed point theorems, so that sequence approach p, but cosine n approach p, right there. Now you see that here we move this one. I mean, think about this. We move p to the left hand side, we're gonna get pn plus 1. This is a minus, not equal sign. Okay, pn plus 1 minus p, and then move pn minus p squared to the left hand side, and then take a limit. Okay, then pn approach, and then also pn approach p, right? Why? Because of fixed point theorems. So here, why fixed point? Why? Because see that g map from here to here, and then what, g prime is bounded by k, right? So we can use fixed point, the result of fixed point iteration theorems, right? Fixed point theorems, and then since cosine n is included pn and the pn approach p, then cosine approach p too, right? So the sequence approach p and the cosine also approach p. Okay, so now then what? Move this one to the left hand side, take a limit on both sides. Cosine and approach p. So we got this g dou prime of p, the left hand side this, over divided by 2 right hand side, right? So now see, look at this. Look at that. What? So the left hand side is exactly the same as the form of the what? Order of convergence, right? Okay, so we see look at the 2. So the sequence is quadratic convergent if g dou prime p is not equal to 0. What if g dou prime p equals 0? The sequence has a higher order convergence. Okay. The g dou prime p equals 0, then why g dou prime p equals 0, then why we're going to get the higher order of convergence sequence? Because here we can add one more, we're gonna get the not linearly Taylor polynomial, but quadratic Taylor polynomials. So we're gonna get third, fourth, maybe, okay, order of convergence, right? The reason that we just expand the g of x in the Taylor series, just linear Taylor polynomial, because we only assume that g prime p equals 0, okay? That's what we got only here. We just expand the g of x as just up to here, okay? If you assume that g prime p equals 0 and g dou prime p equals 0, then we can get the what? This is g dou prime is g dou prime p times x minus dou prime p right there, p, plus, and then g, third derivative, and then cosine. This is a remainder term, okay, over 3 factorial, right? And then x minus p to the third power, right? X minus p to the third power right there. Now this, since g dou prime p equals 0, g prime p equals 0, and then doing this, right? So that you see, let me see, give me a second. Yeah, so we're gonna get third power right there, okay, right here, okay. So now what? We're gonna get the order 3, okay. So now you see the pattern, okay. Now back to here. All right, so now, and then also, so here, okay, not only we get the order, the order of convergence, also we can figure out the upper bound of the absolute error. Okay, so this is bounded by this, right? But we assume that g dou prime is bounded by m, so we got this. Okay, but here, yeah, so this one is bounded by g dou prime. Yeah, okay, yep. So for a fixed point method, see, for a fixed point method to converge quadratically, we need to have both g of p equals p and g prime p equals 0. Okay, so now then, that was really good, really what important assumptions, right? We figured out that g of p equals p and the g prime p equals 0, especially g prime p equals 0. This is really necessary and then important assumptions to get quadratic convergence, order of convergence, okay? So now the easiest way to construct a fixed point problem associated with a root finding problem is to add or subtract a multiple of f of x from x, considering the sequence this for okay, right there. You understand that, right? Therefore, g in the form g of x is equal to x minus pi x times f of x. Okay, right there. Okay. So now then, so what? So now, I mean, what I'm doing, maybe you lost here. Okay. So this is important condition, g prime p equals 0. Now, let's define function g, okay, satisfying both g of p equals p, g prime p equals 0. So now it's the easiest way to construct the function g is what? Let's subtract, or adding of, the something term involving f of x, right? From x. I mean, subtracting or adding something involving f of x from x, right? So now starting, let's just starting from this, g of x is equal to x minus pi of x times f of x. Now let's figure out pi of x satisfying, we just, let's establish pi of x so that this one satisfies this, g of p equals p and g prime p equals 0. Now then right here, okay, find that pi of x such that Pn is quadratic convergent, okay? Then g prime p must be 0, and then g of p is equal to p, okay? So now let's find the g prime p, okay? So g prime p, then what? G prime x gonna be 1 minus pi prime by the, the product rule of derivative. You got this. And then now g prime p is equal to 1 minus this here. And by the way, f of p equals 0, right? Because p is a true exact solution, I mean, exact root, right? So f of p must be 0. So the second term gone. So we got this, pi of p is equal to 1 over f prime p. Okay? now. Let's see. And then now, give me a second. And then also we assume that G prime P is 0, right? Okay. See. Okay. Here, right there. Okay. So G prime P must 0. Okay. So now then pi of x is going to be 1 over f prime x. Then Pn is equal to, give me a second. Right. So now we plug in this one into here. Pi of x, we're going to get this. This is exactly the same as Newton's formula, right? Okay. Right. So first we take a derivative function. We define g as like this to find the f of x satisfying, g of p equals p and the g prime p equals p is 0. Okay. Also the quadratic convergence, so that the sequence is quadratically convergent. That we take a derivative of g, so we got this, and then evaluate g prime at p, so we got this, and then we setting that all equals 0 because g prime p must be equal to 0. And then what, we isolate pi of p, so we got this. And then what? Then pi of x is going to be 1 over f prime x. So we're going to plug in this one into here. Okay, then we got this. This is exactly the same as Newton's method. That's why Newton's method, the order of convergence of Newton's method is 2. So if f of x equals 0, f of p equals 0, and the f prime p is not equal to 0, then for a good initial approximation, Newton's method will converge at least quadratically. Okay, so keep in mind that. So multiple root. Give me a second. Yeah, so I'm gonna cover multiple root next time. Okay, so let me stop here.